Hello, in this video we will talk about isolated systems, but with angular momentum. We have discussed isolated system in the past for energy, for linear momentum. Remember, you always define what your system is. So if you have something rotating, if you define your system in such a way that nothing can interact with your system, you don't allow anything to go in or out, then that's an isolated system. And you might remember from the equations we have discussed before that this is the external torque, and that's the total angular momentum of a system, right? This is the angular equivalent of Newton's second law. So what happens is that if the system is isolated, then there is no external torque, and so the change in momentum is zero. At the end, what you get is that the momentum total vector doesn't change, which means momentum final is equal to momentum initial. So momentum final, if it's a rigid body, right, final is equal to momentum initial, and that's it. Remember, for linear momentum, an isolated system, linear momentum, we had these equations, right? P final equal to P initial, or MV final is equal to MV initial, right? So you see the analogy, beautiful analogies all the way since we started chapter 10. Right, so now let's discuss this. Oh, but I should mention something. Final angular momentum could be a final moment of inertia, final angular velocity, and then on the other side you have the initial. The thing is, the angular momentum can change as well. Let me give you an example. Consider this skater. The beginning, he's rotating with his arms and legs close to the body. So the angular momentum is different because the moment of inertia is small. Remember how moment of inertia, well, depends on not only the mass, but the distance. So when the legs and arms are extended, you have more mass far away from the axis of rotation. If the skater then extends the arms and the legs, what's going to happen is the moment of inertia is going to change. So because what we said here, moment of inertia has to be equal to the moment of inertia. At the beginning, we have small moment of inertia and big angular velocity. That's the initial. After, we have a large moment of inertia prime. So to compensate, the angular velocity has to be smaller, right? And at the end, this product is equal to this product, because we are saying that this system is the guy. There is no friction down here because it's ice. So there is nothing to provide external torque. So the angular momentum gets conserved. Let's consider another case in which you have a nebula, just a bunch of gas in space. So you have lots and lots and trillions of molecules, each one with its own velocity, its own mass, right? So of course I'm going to put just a few. You could calculate the angular momentum of the system, the whole nebula, by just, well, adding all the angular momenta, right? So this one plus this one plus this one plus this one, which is, as we did before, MVR, right? For every guy, for every particle here. And at the end, you're going to get an angular momentum. So if we consider that the system is isolated, so nothing can cross it, right? Give this thing a few billion years, right? Because this is going to be a number, let's say 31 in the k direction, okay? After a billion years, gravity is going to interact, make all the particles interact. You're going to have a grouping, or you what's the word? What's the word I'm looking for? A clump. Let's say that you're going to get clumps of mass because of gravity, and after several billion years, you're going to end up with this, right? In which most particles are moving in the same direction. Let's say the overall was a positive 31, right? So that means the overall angular momentum wins in this direction. So at the end, when you calculate the angular momentum of this using the same equation, you're still going to get 31k. This is, of course, is just a number. It could be any number. But this is a very good example of conservation of angular momentum for an isolated system, right? Initial angular momentum still has to be the same as at the end. So let's talk about this example. We have a star rotating with a period of 30 days about an axis through its center. That's the time interval required for a point on the equator to make one complete revolution. But then the star undergoes supernova, which means it dies and it explodes. And what is left, this is here, it's the remnants. It's also a nebula. We're going in reverse. In the previous example, we had a nebula that condenses into stars or galaxies. Here, a star dies and the explosion creates another nebula. It's called a planetary nebula. There's no planet, but it's because it looks like a circle, a sphere. But at the core, what you have is sometimes you get something like this. It's called a neutron star, and it's very small. This is 10 kilometers only. Before, the star was 10,000 kilometers, right? 10 to the 4 kilometers, right? So now it's just 10 kilometers. And they want us to find the period of rotation of this neutron star. So initially, the idea will be that the system is isolated. No external torque acts on the star. So the moment of inertia initial the angular momentum initial has to be equal to the angular momentum final. We're going to assume, yes, the explosion and everything, but we're going to assume there is no loss of mass. It's a big assumption, but it's a good estimate. For the moment of inertia, we're going to assume it's a sphere. Oh, well, that is symmetrical, and there is some sort of distribution that is going to remain constant. You remember, for a solid sphere, the moment of inertia is 2 over 5 mr squared. For a shell is 2 over 3 mr squared. So we don't know if it's solid, if it's a shell, if it's something in between. So we're just going to call it k mr squared. But the k is going to cancel because we're going to assume it remains the same after the explosion. So moment of inertia initial, whatever k times the mass of the star times the radius initial squared. Oh, actually, I'm just going to call it r squared. Oh my God, squared. And then omega. All of this is initial. And then we're going to have the same distribution, k, same mass, a different radius. So this is radius prime squared, and then omega prime squared. Okay. So What about the angular velocity? Probably you remember there is this version for the angular velocity, which is 2 pi over the period. If you don't remember this equation, look at your equation sheet or go back to I think it's chapter 4 or something like that. Also, this is not squared, it's just prime. So good. There's this to do there. Good. So we can then substitute, instead of omega, I put 2 pi over period initial, and instead of omega prime, I put 2 pi over the period final. So km cancels, 2 pi cancels, and we end up with this equation. R squared over the period is the new radius squared over the new period. So the new period is the old period times R prime over R squared. Final minus over initial. So the period, the period at the beginning, the star was 30 days. The ratio of the radii, we are left with just 10 kilometers, but we started with 1 to the 4 kilometers, and this is squared. So this is going to give us 3 times 10 to the minus 5 days, which is around 2.6 seconds. So yes, neutron stars spin super fast. And it's because of that speed that we can detect them with our telescopes. They generate a signal that we can detect. Stars are composed mainly by neutrons, because everything fuses into neutrons, and because they're spinning so fast, the strong magnetic fields generate beams that we can detect. But anyways, conservation of angular momentum. We'll do other problems in class, but this is a good example.